Okay, so we're going to talk about two specific aspects of atomic size. One, we're going to first of all try to establish how do we define the size of an atom, and then second, what are the trends in atomic size across the periodic table and then going down the periodic table. Okay, so first, just to kind of connect this to something that we talked about in the last unit on electrons and atoms, let's consider a hydrogen atom. Okay, let's just start with the very simplest element. The little red dot here represents the nucleus, which in the case of hydrogen is just a proton. And then this green fuzz that I've got, I sort of hand drew in a cartoon way, represents the so-called electron cloud, right? And so, and we know that the electron in hydrogen in the ground state is in the 1s orbital, right? And we know that s orbitals have spherical symmetry, so it's like a little cotton ball here, right? And the electron density, or that is the probability of finding the electron, essentially as you get away from the nucleus in any direction, the probability of finding the electron goes down. Okay, it gets less and less likely. So the 1s electron very much likes to hang out close to the nucleus. Now, this is kind of the present day quantum mechanical model of the atom. It describes electron behavior in terms of probabilities, and so then when we talk about, well, how big is an atom, it makes it a little tricky. I think you'll see. So it's like, where do you draw the line? If I wanted to draw like a sphere around the nucleus to define the size of hydrogen, how big do I make that? How big do I make the sphere? Because the probability of finding the electron, it goes down as we go away from the nucleus, but it never actually drops to zero. So one way that some people in chemistry define the size of an atom is to establish a boundary, okay, like a shell, a spherical shell, kind of like the skin of an apple, where they say, okay, at this radius from the nucleus, we have a 90% chance of finding the electron. All right, and so they define the radius in terms of these probability surfaces. Okay, which is kind of wild. Okay, well, that's one way to establish R, but I think you can see that the radius that we associate with a hydrogen atom is somewhat arbitrary. Some people might say, well, I like 92%. I think that should be the probability radius. And somebody else will come along and say, no, I think 75% is good enough. So you can see that there can be some room for argument as far as the size of the atom. So what are we going to do? Well, one way that we solve this, or maybe not solve it, but it's a well-recognized approach, is to look at compounds where hydrogen, for example, is involved in a compound. All right, so hydrogen gas is what we call a diatomic molecule. So hydrogen, at normal terrestrial conditions, really doesn't like to travel alone. They like to pair up in molecules where there's two hydrogen atoms bonded together, and so this is what we call molecular hydrogen. And here, when it's in a compound, it provides kind of a handy way of defining the dimension of a hydrogen atom. And what they do is they say, okay, look, we have two. Let's say we got two hydrogen atoms. They're bonded together, and we have experiments where we can actually measure the distance between the two nuclei of the hydrogen atoms that are bonded. And then, if we know the distance, right, the distance between the nuclei, we can establish a radius, an atomic radius, by simply taking that internuclear distance and dividing it in half. right? So this is one way of defining the radius of an atom, right? If you can find a compound where that element is bonded to itself, you can just take the distance between the two atoms and divide it by 2, and you've got the radius. So that's pretty handy. And then that way you can sort of compare the size of different elements on more of an equal footing, right? It may not be the perfect way, but at least it's pretty much consistent. So here are some actual atomic radii defined in this way for several other elements. And the units of distance here, the units of length, is the picometer. All right, so just to remind you, 1 picometer is even smaller than a nanometer. It's 1,000th of a nanometer. So these are really super small lengths. Nevertheless, oxygen is much larger than hydrogen. Nitrogen's a little bit bigger than oxygen. And then as you go down, now listen, let me just pause for a second. If you're watching this video, what I want you to do right now is push the pause button, and I want you to get your periodic table. You'll need to have your periodic table handy here in just a minute. Okay, so now that you got your periodic table, look at these four elements. What do you remember what the name is for these guys? They're in group, kind of over toward the right on your periodic table. They're in group 7A or group 17, depending on what system you're using. And these are called the halogens, right? And you can see that iodine is like gigantic compared to hydrogen, right? And you'll see that as you go from fluorine to chlorine, as you go down the group in the halogens, the atomic size gets bigger and bigger, right? Okay, so here we go. So this is a definition that you need to know right here. So the atomic radius, the one that we'll use in this class, is defined as 1/2 the distance between the nuclei of 2 atoms of the same element when the atoms are joined by a bond. Okay? All right. Now we need to move on to the second aspect, which is the trends in atomic size. So I kind of mentioned one of the trends when we were talking about the halogens on the last slide, right? The size of the atoms gets bigger as we go down a group. So what are the trends? Well, in general, atomic size increases from top to bottom within a group, but here's what's weird: they tend to decrease as you go from left to right across a period. All right. So if we kind of put that in graphical form, so the arrow is trying to convey that as we go left to right across a period, the atoms get smaller, but when we go down, they get bigger. All right. So that's and here's just to remind you, here are the blocks. Here's how the periodic table can be organized in terms of the atomic orbital sublevels. So here, if we start with hydrogen, let's go down the alkali metals. Okay, so hydrogen has one, the electron is in the first energy level, principal energy level. But then as we go down, here's lithium. Now lithium has an electron in the second principal energy level, and so I'm using this kind of cartoonish Bohr model just to sort of convey why the atoms are getting bigger as we go down. They're getting bigger because we're adding more sublevels, adding more principal energy levels, and the higher you go in energy, the further away those electrons are going to be from the nucleus. Okay, and so that's why they get larger. Now, I just want to say, I know that if you're listening closely, up till now, you may be thinking, hey, I kind of get why the atoms get bigger as we go down, but you're not helping me understand why they get smaller going left to right. I mean, that's kind of weird, right? As you go, let's say, lithium to beryllium to boron, you're adding more electrons, right? So why wouldn't it be getting bigger? Okay, that will be in one of the next in one of the next video presentations. That gets a little bit more involved. Okay, so to wrap up, let's just kind of do a quick little check here and make sure we understand the trends in atomic size. Okay, so we're going to play the game, which atom is bigger, boron or oxygen? Okay, well, take a look at your periodic table. All right, so here's my periodic table, and I put a circle around each of those two elements. So what do we know? What do we know about the trends within a period? Because these two elements are in the same period. So as we go from left to right, the radius gets smaller. Okay, so what that means is that boron is going to be bigger than oxygen. And indeed it is. When you look at the data, boron is 85 picometer radius, oxygen 73. Okay, next let's see if you can do this one. How about boron versus aluminum? Okay, all right, now here we see that they're both in group 3A. And so now we can kind of think about trends within a group going up and down. So what do we know about the size as we go down? That's right, it gets bigger, so aluminum should be bigger, and indeed it is. Okay, it's almost twice as big. How about fluorine versus chlorine? Okay, they're two halogens. Same principle as boron versus aluminum. Chlorine is further down in the same group, therefore, you can bet it's going to be bigger, and so it is. All right, now let me throw in one that's just maybe a little bit complicated. All right, phosphorus versus oxygen. So these guys, they're not in the same group, and they're not in the same period, are they? So we got to think about how we're going to figure out which one's bigger. Well, first of all, phosphorus is in it's further down the periodic table, all right? And it's to the left of oxygen. So let's say instead of phosphorus, we can kind of do this in two steps. Let's say we were comparing nitrogen and oxygen, okay? If we were comparing nitrogen and oxygen, obviously nitrogen's smaller, right? Because, I'm sorry, nitrogen's bigger because it's further to the left. The atoms get smaller as we go to the right, so nitrogen's bigger. But we're talking about phosphorus, and since phosphorus is in the same group as nitrogen, we know that phosphorus is bigger than nitrogen, so therefore we know that phosphorus has to be bigger than oxygen, right? Because even if it was one period up and it was nitrogen, it would still be bigger than oxygen. Okay, and then finally, here's an interesting one. I think you'll find this surprising. Let's take something really extreme, like lithium versus astatine. All right, now where's astatine? You know where lithium is. Astatine is way down here. It's just below iodine. Now here you might be thinking, well, astatine is way down the periodic table from lithium. Therefore, it has many more electron shells than lithium, right? And so one would think that astatine would have to be a lot bigger than lithium. I mean, geez, look, astatine has 85 protons, and so it has 85 electrons. Lithium only has 3. Astatine is going to be gigantic compared to lithium, right? Well, surprise. Actually, lithium is just a little bit bigger than astatine. And why? Well, as I said, the trend going left to right, atoms tend to get smaller. All right. Conversely, as we go to the left, atoms tend to get bigger. And it turns out that the size change as you go left to right across the periodic table is more pronounced than the one going up and down, and so you can get some surprising patterns that way. Okay, all right. Thank you very much.